I should talk about functions. Now here, I'm going to prove something about the inverse of a function. Now I'm going to show that to have an inverse, a function must be 1, 1 and onto. Now if you have not heard of 1, 1 and onto before, this is going to sound a bit abstract. But let me start with some examples to explain the meaning of these properties. So let me start with the property of, or the meaning of a mapping. So the usual way to explain this is to think of two sets of numbers. Okay, let me say the numbers here are 1, 2 and 3, and I have numbers here 7, 8 and 9 and maybe 10. Two sets of numbers, and the idea of a mapping is just a rule to relate the number from one set to the number to a number in the other set. So there is, in the idea of a mapping, there is we think of one set as the starting set and one set as the final set. Or rather we can say that one is the first set and the other is the second set. So the mapping is always, the rule is always defined by starting with a number in the first set and then saying which number it should connect to in the second set. So this first set here has a name. It's called a domain. And the second set is called a co-domain. And for example, if the rule is that 2 is related to 8, we say that 2 is mapped to 8. Okay, so that's our mapping. Now, and the rule does not have to be defined for all numbers. For example, my rule can just relate one number here to one number there. And that's it, that's my mapping. So that's a perfectly good mapping, okay, although a bit boring and a bit lazy, since I didn't even bother to think about the other numbers. But it's fine as a mapping. So that's as simple as that. Okay. So now let's look at the idea of. Let's start with the idea of a function. Now, each of these terms that you see here, inverse, function, 1, 1 on 2. Now each of these means something specific about the way this mapping is done. Okay. Now if I start with the idea of a function, let's think about what kind of mapping a function is. Right? Let me go back to this simple mapping. I've defined just this one rule, that 2 goes to 8. Now the easiest thing to understand, easiest way to understand a function is to think about what mapping is not a function. Suppose that I now make up another mapping in which not only 2 is mapped to 8, but another number 3 is also mapped to 8. So now I have a new mapping rule like that. 1 is still not mapped to anything. Alright, I'm not interested in that yet. So both of these numbers are related to the same number 8. Now in this case, we say that this mapping is not 1 to 1. Alright, meaning not one number mapped onto one number, but we can have two numbers mapped onto the same number. So we can say that it's 2 to 1. Right, so actually this is an example about 1, 1. Okay? But I can have another situation in which the one number, okay, is mapped onto, can be mapped onto two different numbers. So if I define my rule this way, that means that 2 is connected to both 7 and 8. So for example, if I ask what is the mapping of 2, the answer is 7 and 8. So with this rule, it means that the mapping is 1 to 2 in this case. Alright, and that's not 1, 1 either. So it's 1 to 2, and this means that the answer of the mapping of 2 is not just 1, but I can have 2 answers. We describe this situation by saying that this mapping is not unique. Alright, unique means just one answer. So in this case, the mapping from 2 to 7 and 8 means that it is not unique. And this idea allows us to define the meaning of a function. A function is a mapping that is unique. Meaning that this mapping gives a single answer in the codomain, or is mapped onto a single element in the codomain. If an element in the domain is mapped onto 2 or more elements in the codomain, it is not unique, and then we say that it is not a function. Okay, so this rule, as I have made up, this is not a function. But if I remove that one, if I remove this rule, so that 2 is just mapped to 8, 3 is just mapped to 8, then it is a function. Okay, so the function must map to a unique number. Okay, so we have defined the function. Now let's go on to the idea of one-to-one. Now, what do we mean by 1-1? Okay, 1-1 is short for 1-to-1. Right? 1-1 is just a quick way to say 1-to-1. Now, I've already briefly said what that means actually. I said that if I have two numbers going to the same number, mapping to the same number, then it is called 2-1 rather than 1-1. So you can guess that 1-to-1 or 1-1 means that each number can only be mapped onto one number can only be mapped onto one number. Another number must not be mapped onto the same number. It must be mapped onto a different number. So that means this is not unique. This is unique, but this is not 1-1. To make it 1-1, I might, for example, have to say change my rule so that 3 cannot go to the same number 8 as 2. So I remove that. So maybe 3 will go to 10. So now I've made a new rule in which 2 maps to 8, 3 maps to 10. So each number maps onto a different number. Okay, so this is called 1-1. So 1-1 means each element maps to a different elements. Okay. Now, before I go any further, let me go back to the function again. There's actually another requirement about the function. I've talked about how a function is a mapping that is unique. So that means that we can't have one element mapping to two different elements. Okay, so that's what this meant. Now, there's another thing about the function, another property that is also required, which is that in a function, every element in the domain must have a mapping. Now, as I have drawn it, you see that I've actually ignored 1 all this time. So 1 is not mapped to anything. Okay, and that is not allowed in a function. In a function, every element must be mapped onto something in the codomain. So that means that even as I've drawn it, let's say 2 mapped to 8, 3 mapped to 10, if I have forgotten about 1, then this mapping is still not a function. So I must map 1 onto maybe 7. Okay, then every one of this has a mapping. So let me write this more clearly. A function is a mapping that is unique. It's a mapping that's unique. And that every element in the domain has a mapping. It's a bit awkward way to describe it, but that will do for now. Okay, now next let me move on to this meaning of onto. Now this is getting quite crowded, so let me draw this picture again. 1, 2, 3, 7, 8, 9, 10. So let me copy over the arrows. 1 goes to 7, 2 goes to 8, 3 goes to 10. So now I have a function. Okay, it is And this function is it is a function because each element maps to a unique one, and every element is mapped onto something. And it is also one-to-one. Alright, each number just maps onto one number, and we don't have two numbers mapping to the same number. Let's look at the idea of on to. What does on to mean? Now, on to means that every element in the codomain is mapped onto. That's where the onto come about. Now let's look at this picture. In this picture, this number 9 has not been mapped onto. Alright, it is quite lonely because all the other elements are connected to a friend in the domain, but only 9 is alone. It is not related to any elements in the domain. So 9 has not been mapped onto. So this particular mapping, defined by these arrows, this mapping is not onto. So in order for it to onto, there must be a number here that also map onto this. And as I've drawn it, obviously I can't have this unless I can, I can, for example, say also map 3 to 9, and then it would be onto. Okay. Yeah, then I have a mapping that is onto. But you have to be a bit careful here, because if I define this particular mapping, then it is a perfectly valid mapping, except that it would no longer be a function, because now I have 3 being mapped onto 2 different numbers. So that means this mapping is no longer unique. Okay, but it is onto. So that's fine as far as onto is concerned. And now let's go back to this thing that I say I wanted to prove in the beginning. It's a proof about the inverse. So now let's look at what it means by inverse. Now the inverse refers to the inverse mapping, which is a function in this case. So let's just think about the inverse function without worrying about the its function property. Now the inverse mapping just means that instead of mapping, say in this case from 1 to 7, I turn it around and map from 7 to 1. In other words, I exchange the role of the domain and the codomain. Alright, so now my mapping is for the inverse mapping simply maps from 7 to 1, 8 to 2, 10 to 3. Okay, and that from the inverse mapping we can get the idea of an inverse function. Alright, and it's by simply saying that the inverse mapping will be an inverse function as long as the inverse mapping has this property of a function, that it is unique and that every element in the domain has a mapping. Now that seems simple enough, except that if the function, the starting mapping is not 1, 1 and onto, it turns out that the inverse mapping is not a function. So let's see why that is the case. Now I've already a picture here about the property of onto. But in this case, this is not a very good example because we already know that the starting mapping is not even a function, since the mapping from 3 is not unique. So what we'll do is this. Let's start by making a function that is not 1, 1. Now the plan here is this. According to this statement, the function must be 1, 1 and on 2 before it can have an inverse. So I'm going to do it by I'm going to prove it by contradiction, meaning I'm going to assume that I have a certain function that is not 1, 1, and then I'm going to show that it is not possible to have an inverse function. And then I'm going to repeat the method for the onto property. So let's start with that. The function that is not 1, 1. Let's make something up. Now, a function that is not 1, 1, for example, let me use the same idea. Example 7, 8, 9, 10. So each must have a unique answer. Right? So this, say 1 goes to 7, 2 goes to 8. Meaning that unique, meaning that 2 cannot go to both 8 and some other number, right? For a function. But if it is not 1, 1, I can have, let's say, the 3 going to the 8 as well. Then it's 2 going to 1. So it's not 1, 1. So this is a function that's not 1, 1. But it is okay because each number only maps onto one single unique answer. Right? So even if I have 2 mapping to the same number, that's fine because each one just goes to 1. So this function, this is a valid function, but it is not 1, 1 because it is 2 to 1. So I have this function. Now, so can this function be an inverse? Or can this function have an inverse? Let us look at the inverse mapping. This means that, for example, 7 would map back to 1, and 8 would map back to 2 or 3. That's the inverse mapping. Now, in this inverse mapping, I will have 8 mapping back to 2 and 3. Right? 8 maps back to 2 and 3 in the inverse mapping. Now, if 8 maps back to 2 and 3, it means that this mapping is not unique because one number maps to 2 possible numbers. And if it is not unique, it is not a function because we have said that a function has to give a unique answer. So in this case, this inverse mapping from 8 gives 2 possible answers. So the answers are not unique, not just one answer. So therefore, if a function is not 1, 1, meaning like here 2 to 1, then the inverse function, the inverse mapping is not a function. So in that sense, a function that is not 1, 1 cannot have an inverse function. So we have proved this 1, 1 requirement for an inverse function. We've just proved it by contradiction. Now let's think about a function that is not on 2. You can actually make use of this same example. Now, this particular function is actually not on 2 because some of the elements in the codomain has not been mapped onto. See, like those two are left out in this mapping. So this is not on 2. So we can also use this as an example for not on 2. If we now think of the inverse mapping again, for this case, think about the inverse mapping for those two elements. Okay, as I said, in the inverse mapping, we turn it around and use that as the domain and map back into that as the codomain. So for the inverse mapping, we'll find that those two numbers are not mapped to anything for the inverse mapping because a mapping has not been defined. Alright, the mapping was only defined for those with those 3 arrows. So only those two elements have something to map back to in the inverse mapping. Those two are not mapped anywhere. So in other words, 9 and 8, alright, there is no mapping for 9 and 8. Now if we look back at the definition for a function, every element in the domain has a mapping. Now in this case, since not every element in this domain has a mapping, therefore this inverse mapping is not a function. So this proves that if a function is not onto, then its inverse, the inverse mapping is not a function. And this completes our arguments that and prove that to have an inverse function, a function must be both 1, 1 and onto.